Hello math friends, welcome to another Math Done Right video. This video introduces the topic of direction or slope fields as applied in differential equations. However, we are going to first dust off the cobwebs of some prerequisite information. When presenting material in mathematics, I prefer to use prerequisite material as building blocks to develop a solid concrete base before scaffolding into abstract thinking. We are going to start by jumping in our time machine to land us in our Algebra 1 class. Now that we are there, let's talk about slope. We're going to start by discussing the definition of slope, which you should remember. When we're talking about slope, we're looking for the steepness of a linear line. A little bit further, if we're given 2 points on a line, x1, y1 and x2, y2, then we can utilize the slope formula, which is m equals y2 minus y1 divided by x2 minus x1 to get the actual numerical value of the slope, which you should remember is rise divided by run. Now, let's take it a step further. There are 4 types of slope. Let's talk about the 4 types of slope. The first is a positive slope. The graph goes up from left to right. As x increases, y also increases. The equation is y equals mx plus b, where m is greater than 0, showing m is a positive number. The second type of slope is a negative slope. The graph goes down from left to right. As x increases, y is decreasing. The equation is y equals mx plus b, but now m is less than 0, showing that m is going to be a negative slope. Next, we have zero slope. The graph goes from left to right, which produces a horizontal line. You should notice that our x values are increasing still from left to right. However, there is no change in y. So that gives us the equation y equals b, where b is the y-intercept of this particular graph. The last type of slope that we will discuss is an undefined slope. This graph goes from up to down, and it creates a vertical line. Conversely to 3, zero slope, you should now see that there's no change in x. So x is now constant, whereas the y values are changing. The equation is x equals some number being whatever the x-intercept is. That will give us the equation of a vertical line. At this point in the video, you should feel all of your mathematical muscles pumping, and you should be giving yourself a pat on the back for seeing everything that I'm teaching as I'm teaching it. So, because you were so good at that simple topic, we're now going to add on a little bit. We were looking at it through the lens of algebra. Let's now look at it through the eyes of calculus. When we are looking for the derivative of a function at a point, would you believe that we're looking at the rate of change of a function at a specific point? What does that mean? Rate of change? We just talked about the rate of change, right? The rate of change would be rise divided by run, which was y2 minus y1 divided by x2 minus x1. But we're now going to kind of make it look a little bit different, just so that it can be scary and you can believe that you actually can't do it when you've been doing it all along. When we're talking about the derivative of a function, we're looking at the change. We're looking at the change in the y values divided by the change in the x values, which is exactly what we've just done. So here we're kind of formalizing it a little bit better. We have f of x plus delta x, so that just basically means the change in x plus whatever the original x was, and then we're going to subtract the first value of x. So that's the exact same thing that we just, I'm saying x but y, which is exactly what we just did in our lens through the algebra window. Okay, so now let's talk a little bit more about the definition of a point. The slope of the tangent line to the graph of the function at that point. So we're looking at a very specific point, an arbitrary point, and we have the corresponding ordered pair as x naught, comma, f of x naught. So simply the x value, comma, y value. From here, we're able to get a tangent line, or we get a tangent line by just running a line through the point, and it's only touching the graph at that point, even though it looks like it's touching it everywhere. That's really what's happening as we drill all the way in. But you should now notice that here, the derivative is really the change that we have been talking about all along. The change in y, delta y means change in y, divided by delta x, change in x. So we have our derivative as f prime x naught equal, again, delta y divided by delta x. Now, I know you're like, what does this have to do with the direction field? Stay tuned. Direction fields are the graphs of differential equations that allow us to visualize possible general solutions. Much greater, we are able to see these graphs due to the collection of line segments, also called lineal elements, that represent the slope at specific points defined by the differential equation. Typically, when graphing a direction field for a differential equation, you will use some form of technology. However, for this example, I'm going to graph it by hand just so that you're able to make the connection between the types of slope, the derivative, and how all of these concepts come together to build such a beautiful graph. Our example is a very simple example, which is very helpful because when we get to more elaborate examples, it is very difficult to try to figure out how to formalize that by hand. You would definitely need technology. Here, I have dy dx equals 1 minus xy. So I am going to choose points that are on the y-axis, the x-axis, the first quadrant, second quadrant, third quadrant, fourth quadrant. And this is this is the strategy that you would utilize when you are trying to get a simple sketch of the direction field. Again, it could also be called the slope field. So I am going to just choose some arbitrary points. I'm going to choose -4, comma, -2. I substitute that into my differential equation. That gives me dy dx equals -7. And I'm going to choose another point. I'm going to choose -3, comma, -2. I'm going to also substitute that into my differential equation. And the differential equation again is dy dx equals 1 minus xy. And I get -5. And then I am going to substitute in -2, comma, -2. That gives me dy dx equal to -3. Then I'm going to choose -1, comma, -2. That gives me dy dx equal to -1. And I'm going to now move into the origin, which is simply 0, 0. If I substitute 0, 0 in, I get dy dx equals +1. And let's say I have 1, comma, 0. Again, since I am multiplying by 0, I get dy dx equals 1 again. And then if I do 2, comma, 0, I get dy dx equals 1 again. So you should be seeing the pattern at this point. Now let's drop to the lower part of our y-axis. And I'll say -1, or 0, sorry, comma, -1. And again, because I substitute 0 in and I have a -1, it simply gives me dy the x equals 1 again. So that means all of our values that give me where I have to multiply the product of x and y, where either x or y is 0, that means that my slope is simply going to be, or the derivative here, is simply going to be 1. So that's very helpful to see that as we go along. So what does that mean? I know that here I have negative 10, 0, I have negative 9, 0. All of these values include 0 for y. That means that we're going to have a positive slope, which is 1. So 1, when we're dealing with slope, remember we were talking about change in y divided by change in x. If I had a slope of 1, I would start from the origin, I would rise 1 and shift to the right 1 and connect those 2 points, and that would give me a line slope of 1. Remember, linear elements are actually looking at the slope of that particular point. So the point is negative 10, 0, so it's going to be a pretty sharp line, and all of these lines should look pretty much the same. And this is the beauty of a simple example, because it's not too difficult to graph, because we're not getting really, really crazy numbers. And these should all be the same steepness, but I'm using a electronic tablet, so sometimes things go off a little bit. But if you're doing it on paper and you want some accuracy, of course you could pull out a ruler. That's nothing that I would expect from my students. And again, you should also know that I have that same slope, direct variation, another term that you've heard before. And I'm not going to go all the way up and down the y-axis, because at this point you should get the idea. So this is the general look on the x-axis and the y-axis. Now let's look at our other points. We had negative 4, 2. So 1, negative 4, negative 2. So from the origin, 1, 2, 3, 4, go up, go down, 1, 2, and we had a negative 7. So that means that that line is getting kind of steep, but it's negative, so that means it's going to decrease from left to right. We just talked about that. And then I have negative 3, negative 2, which is right next door. It's not as steep, but it is still kind of steep, so I'm going to lean it just a little bit. And then we have negative 2, negative 2. I'm going to lean the line even more, because that gives us about negative 3. And then for negative 1, negative 2, I have simply negative 1, which is right at that center. And that just kind of gives you an idea of how you could graph a slope fill by hand. Finally, we will use the same example, but now with technology. In this video, I will be using Desmos. However, I do have a video that teaches you how to program your TI-84 calculator to graph slope fills. I've also included the link that you can type into your own browser to get Desmos slope fill window up and going. Now, with Desmos, this is a set calculator where everything's already here, and I'm just typing in the differential equation 1 minus xy, and you can now see the graph that looks very similar to what we graphed earlier. And that's all.